Okay, so good afternoon, everyone. We are group number 4, and this is our final presentation for the design of a 2 by 2 by 2 cube shape optimization. So we'll just go ahead and get started. So a little bit about our team. My name is Sydney Adams. I'm a junior mechanical engineering major from Chicago, Illinois, and the rest of our group will introduce themselves as well.
I'm Celicia Blyden. I'm a junior mechanical engineering major from North Carolina, and I was also the team leader.
My name is Omazupia Iyoha. I'm a junior mechanical engineering major from PH City, Nigeria.
Hello, everyone. My name is Winston James Jr. I'm a junior mechanical engineering major from South Orange, New Jersey.
Okay, so the objective of the project that we were given was to perform a shape optimization on a 2 by 2 by 2 inch cube to determine the maximum load bearing. So with the final design needed to be 40% of the volume, the material assigned was ABS plastic with a 1,000 pound force applied load, and the overhang needed to be less than 45 degrees. So throughout the duration of this project, the primary tool that our group used was Autodesk Fusion 360, not only for the design and CADing of our final design, as well as using the simulation tool within Autodesk Fusion 360 to perform the various analysis that we did. And lastly, the manufacturing method was PLA 3D printing. So to begin our project, each of our members performed their own individual shape optimization of a 2 by 2 by 2 inch cube in order to select the most desired one that we wanted to move forward with based on the overall results of the optimized shape, as well as heavily considering the highest safety factor. So we had roughly around 4 to 7 optimized shapes that we ended up working with, just as some members ended up performing more than one shape optimization, again, just to get that a variety of options to choose from. And it was not until later on in the timeline of our project that we decide on, as a class, the same parameters that we were going to use for our design. So just initially starting out, the parameters that we worked with, excuse me, for our design was steel as the material with a 1,500 Newton applied load, and the mesh was set to 1%, which you could see as the result here on the right. So based on the shape optimizations, the next step in our timeline was to CAD those designs based on the optimized mesh body, which for the design that we chose to go forward with, you can see as the design here on the left, which we will talk much more into the inspiration with this design based off of this shape optimization going forward. So we used a plane slice to reveal the cross section of our shape optimization with the mesh body that we decided to move forward with, which reveals this internal hollow cavity that you can see here, which played a big factor in how we went forward with choosing further shape optimization and more editing towards our design. And we'll talk much more about that again later on in the presentation.
All right, thank you for that awesome introduction, Sydney. I'll go ahead and piggyback off what you just said. Our design was primarily inspired by shape optimization, and seeing that our load and material parameters were initially undefined, we used steel and loads of 15, 30, and 60 kilonewtons to evaluate our initial safety factor as displayed. Next slide. This led us to further iterations with some key primary changes. Firstly, we implemented a cutout in the shape of the cube's cavity at its top to relocate material needed in higher stress areas, as well as eliminate overhang in our 3D printing process, because there were no supports for the parts that you can see cut out at the top. The walls of the design were also thickened because we kind of got extra material from cutting out that part, and its mass moment of inertia was consequently increased, and hence its resistance to buckling and deformation was better. So we also, could you go back actually? Secondly, we also applied fillets at the 4 vertical edges of the cube to reduce stress concentrations. And we discovered, contrary to our previous beliefs, actually, that the size of a fillet is not necessarily positively proportional to a design safety factor in the sense that instead our iterations actually exhibited a more parabolic safety factor relationship in increasing fillets. So basically, we started from no fillets and reached a point where increasing fillets would just lead to lower safety factors, no higher. And you could associate that to cutting out material or things of such. So we believe that we picked the best iteration. So basically, we were at the top of the parabola in terms of the safety factor iterations. So next slide. We also performed buckling analysis on our design across our several material and load parameters, and results indicated that our design is quite resistant to buckling. Next slide. So in front of you is pretty much a summary of our design and design parameters for reference. So I'll hand off to CC to go on.
So originally we were supposed to use NetFab to create a lattice structure, but as we didn't have access to it, we didn't add it to our main design, but we did create a few structures, a lattice structure design as kind of a backup in case to see if we could get a higher safety factor with them. We had a diamond lattice structure, honeycomb, and cross brace. Some issues we ran into when doing our lattice structures, trying to simulate them, we had a lot of meshing errors and also printability. There was too much overhang or supports, which became a requirement that we could not have. And also one of the designs had like internal supports, which would have been impossible to remove anyways. Next slide. So this was the diamond lattice. This is one of the versions. This is a 9x9 version. We also had a 3x3 version because we weren't able to get the simulation to run on this version because of meshing errors. The safety factor ended up being quite low because there was a lot of stress concentrations in the bars. We tried increasing the radius of that, but it still was too low. And also we tried encasing this inside of a cube as well to help support it, but then that would create the internal supports, which we couldn't have. So.
Okay, so this is the honeycomb lattice structure that Dr. Bay had recommended. We went ahead and we created the cube, but inserted the honeycomb lattice structure. But unfortunately, we weren't able to actually test the structure because of meshing failures, and Fusion 360 kept crashing. And we think it was because of the number of bodies, because there were a lot of, since it's a honeycomb structure, there were a lot of layers to create this cube. As I said, Fusion 360 kept crashing. Next slide.
This was another lattice structure that we made, this cross-brace structure. This is one of the versions of it, the best version, but still with a low safety factor. There was a lot of high stress concentration in the filleted areas. We tried increasing the fillet as well as increasing the thickness of the cross braces, but there was still that stress concentration in those areas, as well as on the top surface and the four areas that didn't have anything supporting it. There was stress concentration on the surface in those areas as well.
Okay, so for our first submission, we had a safety factor of 1.099, and then we were able to increase it slightly to a safety factor of 1.12, and I will speak about how we did that in the next slide. But the question we had was how we could raise the safety factor, and we tried inserting fillets. There was a hidden obstruction that we will talk about later, but and then we tried the lattice structures, but weren't successful with those. So in order to increase our safety factor from 1.099 to 1.12, we added fillets to the inner base. And yeah, well, that's it to the inner base, yes. Okay, so from this image, you can see that our minimum safety factor is located at the in the corner. So we tried to add fillets to the base of our object, but as Zoe said, we reached the tip of our parabola. So adding those fillets only decreased the minimum safety factor, and since we were at the tip, there was nothing else for us to do.
Something we did find when we were trying to optimize our design was that there was this hidden obstruction. We were trying to fillet the sharp corners inside of our design, and I noticed that one of them could not be filleted. So when we took a further look, we realized there was this hidden structure. We deleted it and filleted that corner. However, it didn't change the minimum safety factor because it was due to that edge.
So we our final design, the material we used was ABS plastic with a safety factor of 1.12, and our final volume was 3.2 inches cubed, which was 40% of the original volume. And here are two photos of Dr. Bay 3D printing our design. And that is all. Thank you.
Thank you for your presentation. Do you have any question?
So I have a quick question. So what is the reason of choosing 1.12 safety factor?
That was the result from our simulation. If you look through the slides, it does seem like we have higher safety factors, but that was before we changed the parameters, so our material was steel. But once we changed to plastic and 1,000 pound force load, that was our highest safety factor.
Okay, thank you.
Rachel, do you have any question?
Yeah, so if you've had more time or have been able to be in the lab, are there any other structures that you would have liked to explore aside from like the honeycomb type of structures and the diamond lattice?
Well, there were other various types of lattice structures that we saw when finding the lattice structure, so we possibly could have found one that would have been 3D printable and had less overhang to try. Maybe that could have had a higher safety factor, but not had the issue of not being able to be printed.
Okay, so any other question? Yeah. If not, thank you so much, and let's move on to the next group.